Hi, I am Mustafa Aker. I am a Master of Science student from Istanbul Technical University in Department of Computer Engineering. Today I am going to present you a paper which is called A Comparison of Different Embedding Methods on Session-Based Recommendation with Graph Neural Networks in collaboration with Cagri, Emre, Yildiz and Yusuf Yaslan from the same organization. So, here is our agenda that describes the outline of this presentation. First of all, I will give you a brief introduction, including the definition of the problem that we are aimed to solve, our purpose, the method that we have followed during our study, our motivation, point of origin that why we are trying to challenge with this problem, and finally, our ultimate goal that we want to achieve at the end of this study. Then, I will give a gentle introduction to recommendation systems and session-based recommendation systems, including recent works on session-based recommendation systems, which are called NARM, STEM, and SR-GNN. Then, I will give a brief introduction to the embedding scheme, including what is embedding and what are the embedding types that we have used within this study. Then, I'm going to talk about the experiments that we have conducted during this study, including the datasets that we have used, evaluation metrics that we have used as a performance criteria, and the results that we have observed. For the last, I will conclude the results that we have derived from the experiments, and I will talk about the ways that how this study can be improved further by the interested researchers. Our presentation ends with references that belongs to the resources that we have used within this presentation. Okay, first of all, let me try to explain the problem that we are aiming to solve. Basically, we want to predict and recommend the next item only based on previously selected items. Our purpose is introducing new session-based recommendation model to predict users' next behavior. In order to realize our purpose, we have made a modification on existing state-of-art session-based recommendation model, which is called SR-GNN, GNN's embedding layer, and observed the results that we have get. Our motivation upon this study is we believe that replacing the current embedding layer of the SR-GNN model with the new embedding types will boost the performance of the existing methods. Finally, we can describe the goal of this project as observing effects of the different embedding types on session-based graph neural networks recommendation systems. Now let's talk about recommendation systems and session-based recommendation systems with their definitions, similarities, and their differences. Basically, a recommendation system can be described as methodologies that suggest users the most relevant items depending on the data that collected belongs to a specific user. Now, let's talk about recommendation systems and session-based recommendation systems with their definitions, similarities, and their differences. Basically, recommender systems can be described as methodologies that suggest users the most relevant items depending on the data that collected belongs to a specific user. Session-based recommendation systems are similar to traditional ones, however, they also rely on long-term and short-term attention. This term corresponds to consideration of items appearing in a session at the first places and the last places with some waiting operation. The effect of the item that comes lately in the session will affect the result more with respect to the items that have seen firstly. Moreover, there is no profiling operation carried out within a session-based recommendation, which means each session treated individually. So, there is no cold start effect observed for the sessions that we have been executed on the first places. Session length is a term that comes with a session-based recommendation models, which helps us to describe relations among items with greater values of this length. History of session-based recommendation systems start with early 20s, and number of models offered in this field grows rapidly almost 10 years later within the new developments in deep learning field. Studies that form a baseline upon this study come up with 2017, 2018, and 2019. First one of these studies, NARM, applies an encoding layer with an attention mechanism to the model user's behavior. The next one, STAMP, proposes that long-term memory may be insufficient for long sessions, so a short-term attention mechanism is introduced as a solution. For the last one, SR-GNN also applies a long and short-term attention mechanism, but this time sessions are treated as undirected graphs represented with their adjacency matrix. Embeddings of these graphs are given as an input to the gated graph neural network layer. This is a general overview of SR-GNN by illustrating like a flow diagram. As it is seen, overall SR-GNN model contains two main parts. First part is an embedding layer, and the second part is a graph neural network layer. At the first place, sessions are described with their adjacency matrix and an embedding operation applied to this matrix to generate input data to give an input to the graph neural network layer. We will examine this process in details later. After embedding data of each session given to gated graph neural network layer, after that, the effect of long and short-term attention added to the processed data. This operation basically simulates the interest of the user. Lastly, obtained results are passed through the linear transformation and softmax layers consecutively in order to get prediction results from the overall network. Okay, let's come to the part that describes our contribution to the current model. As I said previously, a vanilla SR-GNN model comes with two major parts, graph embedding part and gated graph neural network part. Our study mainly focused on embedding layer of the current model. The original SR-GNN calculates each node's embedding value as normalized weights of neighboring nodes. In our study, we have replaced the current embedding technique with different embedding techniques while hoping to represent nodes in a better and more meaningful way. As I said before, this is the original SR-GNN model overview. And this is the exact part that we have performed our research and conducted several experiments. After we get the results from our embedding layer, we have fed the original SR-GNN's graph neural network layer with these obtained embedding values. After all network completes its job, we collected overall results and compared with the results of the original SR-GNN's results, hoping to get better performance values. Before we deep dive into our experiments, I want to give an explanation about what is embedding and what are the embedding categories are known mostly. Embedding term corresponds to mapping the data from one vector space to another, mostly from lower dimension to higher one. In addition to this definition, for basic understanding, it's possible to liken to projecting the vector to another dimension. Graph embedding scheme adds a new perspective to embedding scheme by operating on adjacency matrix of a graph. This process deals with representing each node in a graph as a vector by considering their neighborhood with other nodes. There are several ways to convert nodes into vectors. First methodology that subjected by this study is metric factorization-based methods. This category consists of operations based on eigenvalue, eigenvector, and decomposition calculations. The second category is random walk-based methods, which generates embedding values of nodes by graph diffusion algorithms. For the last embedding category, deep learning-based embedding category has been taken into place. Within this perspective, embedding of each node is learned by adjusting weights between hidden layers of deep learning model by feed-forward and backpropagation operations. For the experiments section, a singular value decomposition and a Laplacian eigenmaps are selected as matrix factorization-based methods. Word-to-vec, node-to-vec, and deep walk are picked as random walk-based methods, and line has been chosen as a deep learning-based method. For the datasets and data preparation part, we have fundamentally used two different datasets, which are called Yildiz and Diginetica, that are belongs to two specific e-commerce websites. These datasets are also used some machine learning and deep learning challenges, such as Rex's challenge. For Yildiz dataset, it has almost 80 million sessions and 40,000 nodes, and for the Diginetica dataset, it has almost 20,000 sessions and 45,000 nodes. Since full Yildiz datasets have requires huge processing power, we have reduced the size by its 1/64 due to our resource limitations. Before we work on these datasets, we have followed some preprocessing steps with original SR-GNN model. First of all, we have serialized session nodes with respect to their timestamps. Then, sessions that having single item have been removed. Finally, items that appearing less than 5 different sessions are removed. As performance evaluation metrics, we have used similar performance metrics that have been introduced and used with original SR-GNN. These metrics are called recall at 20 and mean reciprocal rank, also called MRR, at 20. Recall at 20 metrics refers to the ratio of correctly proposed items that occur inside the top 20 prediction. Here, top 20 prediction term means that the first 20 items that ordered in a descending manner by their probability to be offered by the prediction model. MRR at 20 metric is referred to average reciprocal ranks of the items that have been correctly recommended. This term can also be described as distance to the perfect prediction. Okay, now it's time to talk about the experiments that we have carried on within our study. For each dataset, we have set up 6 different execution environments, which corresponds to 12 at total, and try to show the effect of the application of different embedding types on original SR-GNN model. Basically, we have generated corresponding embedding data for each dataset, and gated graph neural network layer of the model is fed by these obtained data. Now, let's talk about results that we have collected from different experiment setups. As it is clearly seen, all performance results in terms of recall at 20 and MRR at 20 are very close to each other, and also original SR-GNN results for both datasets. Specifically, you choose dataset, none of the embedding methods could get better recall at 20 value than the original SR-GNN embedding method. But in terms of MRR at 20, withGraph has slightly outperformed the original one. For the Diginetica dataset, again, SR-GNN with applied differing embedding techniques did not able to show better performance than the original one in terms of recall at 20 and MRR at 20 both. These graphs show the result of each execution together while comparing them with the results of the original SR-GNN. For the last part, let's conclude our results and experiences that we have gained with this research study. As it described previously, withGraph performed head-to-head with original model for Yusuf's dataset. For the Diginetica dataset, Laplacian eigenmaps has showed almost same but slightly less performance with original model while clearly outperforming other introduced embedding models. For the withGraph method, Yusuf's dataset has longer average session length than the Diginetica. This might be the reason that withGraph has approximated more closely to the original model within Yusuf's dataset. For generalization, all embedding methods show similar but less performance than the original embedding technique, other than withGraph. So, characteristics of dataset plays a key role within this study. However, complex embedding techniques require more computation power but does not improve the performance as expected. For future researchers, we believe that there exists a way that getting better performance results than original SR-GNN model by calibrating its embedding and neural network layer. Adjusting learning rate of the model, changing hidden layer size for better representation, and fine-tuning embedding size of nodes are all good starting points for future works. Also, using different datasets except that you choose and Diginetica might result in better performance results, since each embedding method can cover different characteristics of datasets. Thank you for your time.